Okay, let's close out section 1. First, here's a summary of all the truth tables we have all in one spot. You can find this in the notes. Here's how we're going to symbolize some of the following propositions. I will take the job if and only if it pays well. So I underline the concept as long as it's understood. So I will take the job is T, pays well is then P. As if and only if, it's the biconditional. I will take the job if and only if it pays well and Joe is my boss. This is understood to mean that you need to meet both of the conditions, pays well and Joe is my boss. So note that here when I go to symbolize it, I put P and J in parentheses to say this is a package deal. You need to meet this first. I will take the job if and only if it pays well or Joe is not my boss. Now here, you could let J stand for the proposition Joe is not my boss. That's just going to get confusing down the line. The natural order here is to go with Joe is my boss as J, and to have the negation be Joe is not my boss. So now we're going to look at some compound propositions, and our goal is to construct a truth table for some of the symbolizations we did before, where we have more than one logical operator to deal with. So let's look at this one. We want to come up with a truth table assignment for P and not Q. So we start off here. I have the possible different assignments for P and Q separately. And let's run through the list here. The first thing is to note that we're going to do these operators one at a time, following a sort of order of operations. The first one we're going to do here is not Q. So I take the truth table assignment of Q and I negate it. I put a 1 at the bottom, and I want you to do the same when you're doing truth tables. Say this is the operator that needs to be cleared first. Next, I look at the and. I can now look at the column with the underscore 1 there and compare that with P and follow the truth table assignment for conjunction. So I end up with the following, and that's the last operator cleared. So this is the truth table assignment there under 2 for the entire statement, P and not Q. When you introduce a third variable, you end up with many, many more combinations. I do want to point out the pattern here. So 4 trues in a row, followed by 4 falses in a row for the first variable. Then you alternate 2, 2, 2, 2, right? True, true, false, false, true, true, false, false. And then finally, your last variable alternates every other. Looking here, which operator do we need to clear first? The and. So we look at the original truth value assignments for P and Q and list them there. Next, we're going to tackle the implication. Be careful when you're tackling these implications. It's easy to get wrapped up and look at R and then the and there because they're listed. You know, we're used to reading left to right. But notice the way the implication goes is that on that first row, for example, I'd want to do true implies true. Well, that's true. The next row there, I'd want to do true implies. Let me go ahead and reveal that. So right here, this comes from the true implies true. The next row, I have true implies false. So again, I'm having to read it because this part comes before this part. So I end up with, this is the second operator I've cleared, and this is the final truth value assignment for this operation P and Q implies R. Take a look at a slightly larger one. So here we have lots of operators going on. The crucial part here is to do it in the correct order and figure out which assignment I want to do first. Well, just like regular order operations, I'm going to start here in the parentheses. I'm missing a parenthesis there, I apologize. I'm missing one right here to close this out. You can see this in your follow along notes, I apologize. So the first one I'm going to do again is this negation symbol. Then I'm going to move on. I'm going to tackle the and. Then I'm going to tackle the biconditional. Then I will be ready to do the negation. So it says 4 operators, so I get 4 steps to complete. Next, in your follow-along notes, you'll see that I have a whole list here. It goes over what I said about alternating the trues and falses, how many rows you want to do, and then goes over how to create these tables. I'm not going to read this to you. You can just go to your follow-along notes and read it. Let's take a look at not P implies Q. How would I do this if it was just a blank page? What am I going to do? So I'm going to start by creating my table. It's got 4 rows. I write the statement at the top. And then what I do to cut down on time even more is that underneath the P and Q, I write the possible assignments. This gets complicated if P and Q shows up multiple times, but if you can organize on the paper well, this works out. Now I'm ready to do the first operator. That's going to be the negation. Then I close out by doing the implication. Not P and not Q, sorry, P and not Q negated. It's important to try to read it that way because it gives a hint as to what order I'll be doing these operators in. Again, let's give my total combinations for P and Q as inputs. Run through here. I'm going to start with the negation. I'm going to do the and then I'm going to do negating the entire thing. I'll be negating column that is labeled 2 there. Here's an example for you to try. I'm going to slowly reveal it, but take out a sheet of paper, give it a shot, and see how you do. This is the final truth table assignment I get. It's big, it's cumbersome. Hopefully you put in enough reps that you'll just start to see the connections here. Oh, that's how an OR works. This is how a negation works. But you can always just go back to the summary of truth value table and just see it literally as a matching game if you need to. One other thing to note here is that you can do logic and bit operations with these. So if you let the 1 bit be true and the 0 bit be false, you can quickly do these logical operators in binary, as it were. So a bit string is a sequence of 0 or more bits. So the truth table here can go really, really fast. I'm going to show you how to do both a bitwise OR, bitwise and a bitwise exclusive OR. The bitwise OR simply asks, hey, sorry, I paused here. These are brand new slides made for the course, and so something is incorrect here. It's this one. This should be a 1. I apologize. So in your notes, you'll see that this right here is a 1. I was going to say it's really simple because doing a bitwise OR, you're just asking, are either one of these a 1? Sure enough, again, if I hadn't made a typo here, they're both 1s. So yeah, or either of them a 1? Yep. Here's the first proper one we can see. This one is a 1, this one is not, so the bitwise OR gives me a 1. Bitwise AND requires both of them to be 1s. So again, with a correct assignment, I'm just going to move over to this column. We can see a 1 and a 0. They're not both 1s. So I get a 0. A 0 and a 0, 0. They're both 1s. I get a 1. And finally, bitwise exclusive OR, only one of them can be a 1. So we see here, 1 and 0 gives me 1, but 1 and 1 gives me a 0, because only one of them can be a 1 to satisfy the exclusive OR.